right, hello everybody, and welcome to chapter 13, section 1. This is the first part of 2 parts of lecture. We're going to go through just the first 2 topics in this chapter, the first being dissociation, and the second being solubility and precipitation, and how to predict if something is soluble or not is a quick review in this particular lecture. Our next lecture video will be on net ionic equations and electrolytes, and how to predict the products of reactions when it comes to those double displacement reactions we talked about in the past. So let's get started. First thing that we're going to talk about is dissociation itself. It's a fancy term for splitting apart, where ions that are going to be present in ionic compounds break into their 2 different charges, the cation and the anion. Now, one of the things to remember, and there's quite a few, is that these are ionic compounds formed by a metal and a non-metal. Now, sometimes we can form them directly with just a metal and non-metal element. We can also form ionic compounds with a positively charged metal and a negatively charged polyatomic ion. And then we can also form ionic compounds with positively charged polyatomic ions and negatively charged nonmetals. Or we can even have a combination of 2 polyatomic ions. Now, one of the things I do want to remind you about from way back when, and this is probably last semester, is that when we form ionic compounds, we balance the charges. So the overall compound has a 0 charge. Okay, and we'll look at some examples here on the next slide. So the first one that we're going to look at is NaCl. Now, Na and Cl, when they join together, Na is common charge, and I'm going to have to remind you that there are common charges on any of our polyatomic ions you should have memorized, and that there are common charges on the different elements on the periodic table. So a couple of things that might be handy when you're doing the problems in this chapter are a list of polyatomic ions, and a periodic table. Okay, so in the case of NaCl, we know that Na has a +1 charge. We know that Cl has a -1 charge. If we wanted to form a compound from that, we do that crisscross method, and we're left with Na1, Cl1, which when we write overall compounds, we drop the 1s. Now, the new stuff in this chapter says what happens when these ionic compounds dissociate, and that means break apart. So over here for our first example, we have the simple ionic compound of NaCl, so table salt. When you add it to water, so these arrows in our dissociation equations now mean add to water. All of them mean that. So this means add water. Okay. When we add this to water, the Na ions and the Cl ions are going to break apart into their individual positive and negatively charged ions. That AQ means dissolved in water. All of this is review. We've talked about this stuff before. All right, so the next thing I want to point out on this particular reaction is how this works with molar amounts. And remember that all of our equations can be balanced, and in order to balance this particular equation, we would have to put a 1 in front of each thing. So if we took 1 mole of this particular reactant and we dissociated it, it would produce 1 mole of one thing and 1 mole of the other, because those are the numbers that are in front of our balanced chemical reaction. So in here we're going to see how this balancing has to happen when we do this dissociation thing. So in our next example, we have calcium chloride. This calcium chloride, when it's all together as a solid, when we add it to water, we're going to get the calcium 2 plus ion. Where does the 2 plus come from? I'm hoping you're saying it out loud or you're thinking it. The common charge on the periodic table. Where does the -1 come from? Same thing. Why is there a 2 in front? Because when this breaks apart, chlorine likes to be by itself, for one thing, and it will have a 2 in front. Because there's 2 over here, there have to be 2 over here when we balance the equation. And when we talk about molar amounts, if we had 1 mole of this and it broke apart, it would create 1 mole of just straight calcium ions and 2 moles of straight chlorine charged ions. All right, that brings us to our first lecture question. The first question says, tell me why 2 moles of chlorine was produced in the second example. If you aren't sure what the answer to this is, I'm going to point you backwards to our slide and maybe listen. The other one is going to say, write the dissociation equation for this compound. This compound is aluminum, symbol Al, chloride, symbol Cl. When you're done with that, go ahead and move forward. Our next dissociation example is going to come from polyatomic ions. So like I said, there are several types of compounds out there. One of them is going to involve our polyatomic ions. When we see those things in parentheses, sometimes they're not in parentheses, you have to identify them, but when we see them in parentheses, we keep them together. And we have to recall our charges on polyatomic ions. So for this first example, we know that silver is a +1 charge only because we know that nitrate, we know that nitrate is a -1 charge. So since this is, because this has to be, -1, Ag must be +1. This is why memorizing your polyatomic ions comes in handy. Those of you planning to take the dual credit class next year, this is an expectation that you remember your polyatomic ions always. All right, and just to kind of reiterate what we talked about on our previous slide, the numbers in front of our balanced equations are going to be what actually determine how many of each are going to be made when they break apart. So 1 mole of this compound breaks into 1 mole of just the silver and 1 mole of just the NO3. And this is a huge misconception for a lot of students. So what I'm going to do is I'm going to draw a picture to help you understand how this works. On the left side of the equation, we have something that has 2 parts. So we've got the Ag is the empty circle and the NO3 is the filled in circle. When that breaks apart, it's going to make 1 Ag and 1 NO3. Okay. Now, if I did this 10 times, I would end up with 10 of these and 10 of these. If I did this 75 times. So if I had 75 of these molecules, it would break into 75 of these and 75 of these. Okay, think about it like a piece of puzzles that actually breaks apart in the way it's supposed to. 2 pieces of a puzzle you can break apart. All right, the next example has the ammonium being the positively charged ion. You would have to know either, in this case, that the sulfur has a common charge from the periodic table of -2, and this is pretty much an always situation. And you would have to know that NH4 is a +1 and it's a polyatomic. So that's a common charge. And remember that when it comes to balancing this particular thing, in order to make a compound from these 2 things, we would have had to do the crissy-crossy, right? And that happened for you in these particular equations, but I do just want to point them out. This is how we get our balanced equation. or our balanced compound that is not charged. Okay, just remember how to do that from way back when. Up here, why did we not automatically assume that the silver was a +1? Because this is a transition metal. Remember, transition metals have several different charges. You cannot assume what that charge is, okay? Now, when we broke this particular compound down into its parts, 1 mole of this has, in this case, 2 NH4s and 1 S. So when we break it down, one of these will break into 2 of the NH4s and 1 of the S's. Okay. Now, if we then again use our particle model, that's what this is. If we say we have 10 of the particle models, then we're going to get 20 of the individual particles and 10 of the S particles. Okay, so hopefully we understand that in this particular case, the empty circle is the NH4. You'll get 20 of them because you'll have started with 10. And when we balance the equation, we use those coefficients to figure out how many we're going to end with. So 1 mole of this produces 2 moles and 1 mole. Okay. Again, think about what happens if we break a 3-piece puzzle into its 3 parts. We're going to get a 1-piece thing, a one big structure becomes 3 different pieces. Okay. All right. And here's your next question. I'd like you to write the dissociation equation for this particular compound. When you're done, you can go ahead and move on. All right, the solubility and precipitation reactions are the second topic we're going to cover today. And one of the things to note is that there are varying levels of dissociation ability for each individual compound. We call that a solubility. So how good the thing is at dissolving once it hits water is called that thing's solubility. And in this class, we're going to label things as either completely soluble, so they break apart when they hit water, or completely insoluble, so they stay as solids even in water. So what we're going to look at, and I'm going to remind you because we've seen this chart before, we've seen like kind of a more difficult version of this chart, is a simplified version of the solubility rules. These are just going to be a really quick summary. Typically, I would make you memorize these if you were in my dual credit class. So next year, you will be asked to memorize these if you're in that class. But for now, you're going to be able to have this in front of you when you're doing your homework, when you're taking your quizzes, or when you're doing anything related to the solubility of a compound. So these are just the general rules that tell us why things will dissolve or not dissolve when they hit water. And when we talk about solubility, one of the things I really want to point out is when we say something is soluble, that means it dissolves in water. So it forms a colorful solution, or it forms a clear solution where you can't see the particles. That's also an option. That would be something that is soluble. The other option is an insoluble thing that forms 2 layers or forms a solid at the bottom of our solution in general. And over here we have some examples of them. So now what we're going to do is we're going to learn how to use the chart that we were given, and I've copied it over here, to determine if something is soluble or insoluble in water. Okay, and our first one's going to be NaCl. Now, I know that this is soluble in water. You know this is soluble in water. Our goal is not to just label it soluble or insoluble. It's also to tell ourselves or to give a reason why. And we're going to refer to these 6 rules as our reasons why. So for number 1, I'm going to predict that NaCl is soluble. And I'm going to predict that because of rule 1. Rule 1 says sodium, potassium, and ammonium compounds are soluble in water. No exceptions, no anything else to think about. Okay. Rule number 2, or I'm sorry, the second one that we have is lead chloride. Now it says, I'm going to say that this one is insoluble. And this is going to be because of number 3. Number 3 states that most chlorides are soluble, except those of silver, mercury, and lead. It does say that lead 2 is soluble in hot water, which is what this is, but we don't have hot water. We were just asked to figure out if it was soluble or insoluble. So for us, we're going to say insoluble, and we're going to say because of rule 3. All right, our next one's going to be silver phosphate. And silver in this case is a silver 1. I'll remind you that when we do these, remember we can do the backwards of the cross method. There should be a 1 there. What we end up with is Ag1 plus and PO4 has a 3 minus. That's not what I'm looking for, but that does tell me that silver has a 1 plus charge. And since silver is a transition metal, that's how I can figure out what the charge is. If you look back up at rule 3, it did give us mercury 1 and lead 2. So there are some things we actually have to worry about when it comes to the charge on the metal. All right, so I'm going to look for phosphates on this chart because I don't think silver's on here. And in rule number 5, it says that phosphates are insoluble unless they are attached to sodium, potassium, and ammonium. Well, this is a phosphate, and it is not attached to sodium, potassium, or ammonium. So this guy is insoluble. And I'm going to say because of rule 5. Okay, let's do the last one. Last one says potassium phosphate. Potassium is a common +1 charge. Phosphate is still a 3 minus charge, hasn't changed. And I'm going to go back to rule 5 and I'm going to say, oh, look at that. It says phosphates are insoluble unless they have sodium, potassium, or ammonium. In this case, this is one of the exceptions. So this guy is soluble because of rule 5. Moving on. Your lecture question for today, the last one, this is rule 5. Rule 4 is to use the method that I just talked about. So tell me if it's soluble or insoluble and tell me which rule makes it that way. And when you are done, you can move on. This is actually the end of part 1. Part 2 will be uploaded later.